Hello and welcome back. In this example, we're going to be using a fundamental theorem of calculus to find an integral that has a change in its definition. And the idea here is that if we look at the graph of this function, and we've seen plenty of these before in either college algebra or pre-calculus, this is a V shape at 1, and it's going to be above the x-axis. And we're trying to find the integral that starts at 0 and ends over at 2. So right there at 2. Of course, not a symmetric picture, but still good enough. So the idea here is that for this function, our absolute value graph changes at the point x equals 1. On the right branch of the function, it's just equal to the positive x minus 1 definition. And you notice it does have a slope, and if you were to continue to draw the graph, it would cross the y-axis at negative 1. On the other branch of our function, you will notice that it's actually the opposite of that. It is the opposite of x minus 1. So therefore, when we go through and use the fundamental theorem of calculus, we have to split our integral into two halves, or two parts, I should say, not necessarily halves. So the integral from 0 to 2 of the absolute value of x minus 1 dx is going to be the integral from 0 to 1 of that negative branch, plus the integral from 1 to 2 of that positive branch with respect to x. And this will give us the area of our integral. So next thing to do, apply the fundamental theorem. We know it's going to be the opposite of x squared over 2 minus x, evaluated from 0 to 1, plus x squared over 2 minus x from 1 to 2. And we can now evaluate these individual parts. That's going to be the opposite of 1/2 minus 1. And then we subtract at 0. Doesn't really contribute anything. And then back here, we're going to have 2 squared over 2 minus 2 minus 1 squared over 2 minus 1. And that's going to give us a negative 1/2 plus a 1. And then we're going to have plus 2, and then a minus 2, and then minus a 1/2. And that is, let's see here, that's not correct, is it? No, because if I look at this, that is a plus 1 over there. So I forgot that one extra term. So there's a plus 1. So again, negative 1/2, plus 1, plus 2, minus 2, minus a half, plus 1. So a lot obviously cancels in this. We can lose our 2 halves with our 1. We can drop out the 2's, and we are left with exactly 1 unit of area. Let's go back to our graph and see if that makes any sense at all. Well, this right here is a triangle, which is 1/2 base times height. So it actually has an area of 1/2 in it. And this triangle right here also has an area of 1/2. Again, these are not to scale. So summing up the area of these two triangles, we do get 1 unit of area. So again, we probably could have just used simple geometry for this problem, and that's what you would do in practice. But the idea here was to illustrate the application of the fundamental theorem of calculus. We already had to split up our two parts of our integral into two separate parts so we can find it. And again, this is very important to make sure that anytime you are trying to find an integral, that you're always using the right part of the right function.